Oh, good morning, everyone.
Good morning.
Good morning.
Good morning. Good morning.
Good morning, Mr. Taffa. How are you?
I'm doing good. We are in lockdown
Thank you.
in Kathmandu.
Okay. Thank you.
How is the situation in Afghanistan, Kabul?
Here is not lockdown. Here is normal.
Normal.
About normal.
Nice.
Okay.
I don't know if anything's normal, but
Hello, everyone. So we're just going to wait a few more minutes for everyone to join. We have 19 people so far in the meeting, and I think we're expecting about 10 more. So if everyone's not here within the next 5 minutes, we'll just get started without them. Okay, Rajesh, do you think we should get started, or should we wait a little longer for more people to join the meeting?
Yeah, I think we should start.
Okay, cool.
Yeah.
We will get moving then. So, and just as a reminder, this is recorded also. So anyone who, if you have connection problems or if your friends were unable to get here at the start of the meeting, they can watch the beginning portion online on YouTube. So to kick it off, we're going to do another question and answer session with Carl on his lecture material from the lecture he posted online a few days ago. The lecture for today's topic was on snow water equivalent reconstruction at the spatial scale of MODIS tiles from a full country to all of high mountain Asia. Kind of looking at what we did in the lab last week with the point energy balance model, but using MODIS data to do this at scale. And Carl also talked about our methods we use to map snow at high resolution from space with satellites, and how we can not only measure the area that's covered by snow, we can also measure the physical properties of the snow from space, both how reflective it is, and we can account for the fact that sometimes trees obscure the view of the snow, and the satellite doesn't always have a good view of it. So to get started, we're going to open it up to another Q&A session. So if participants could write their questions in the chat box, and then Carl and I will go through and we'll respond to your questions that you have on both the lecture, any of the lectures up to so far, especially the last lecture. So go on and feel free to send your questions on over to us.
And while you're thinking of your questions, I'll ask one to start us off. What part of the season can the reconstruction be used for? Does anyone remember that one?
Feel free, you can either unmute yourself or you can just type your answer in the chat box. So this is one of those SWE products we've been talking about where they all have different instances when they're better or worse and a better choice. And so for the SWE reconstructions, there were some very specific constraints on the time of year that it's useful for estimating how much water's in the snowpack. So does anybody remember exactly what time of year we can use the SWE reconstruction data for estimating snow water equivalent?
And the word reconstruction might give you a clue. Well, it's Monday and everyone might not have had time to watch the lecture, so I'll go ahead and answer that. It's during the melt season. So we can't look at the accumulation part of the season when we're using the reconstruction. We're starting at the end after all the snow is melted out and reconstructing back to the maximum snow water equivalent.
Yep. Yeah, and so this reconstruction that Carl's talking about, so yeah, and so we just got a message in the chat box from one of the participants that, yeah, for Afghanistan, this would kind of be from mid-April till about June is the time of year when it stopped snowing and the snow is melting out. So that's correct. That's the reconstruction. So for Afghanistan, reconstruction is a very useful tool for those months of the year. And today's lab, we're actually going to be showing reconstruction in various years in Afghanistan. And kind of while we're waiting for more questions to come in, we'll just talk a little bit more about this method that we've worked a lot on. And it's kind of a combination of both really high resolution and high quality snow mapping, where Carl in his lecture, he talks about the methods we use to get continuous maps of snow cover every day from the MODIS satellite, where we can account for both the fact that clouds get in the way of seeing the snow sometimes, and trees can also get in the way of seeing the snow. So we have ways where we can account for those two things, and Carl goes into detail in his lecture. And from that, we can get these maps of the snow cover extent every day. And in addition to that, with MODIS, we also can derive the properties of the snow from the satellite. And the two properties being the grain size of the snow, and then how many contaminants are in the snow. And it's the combination of both how large the grains of the snow are and how dirty the snow is that lets us know how reflective the snowpack is. And that's the really key driving property of the snowpack that we use for these SWE reconstructions, where we can figure out, okay, we know how much energy is going into the snowpack. We know how much snow cover we have. If we know how reflective it is, we can really figure out how much is melting every day. And to just give you guys a quick kind of example of how we use this in our work, while we're waiting for more questions to come in, I'm going to share my screen really quick. And I'm going to show you an example in a paper we just published that shows.
Sorry.
Yes.
I have a question that the melting of snow, in some topics I have seen that normally they are taking about 0.5 centimeters, I mean half a meters per day. Is it without rain or whatever, volcano or some other things which happen, which cause that melting of snow as taking speed. So is it okay for every places, 0.5 centimeter, I mean half a meters melting of snow?
Half a meter would be a lot. Usually it's not melting that quick. You would first need a ripe snowpack, and you would need a lot of solar radiation. I'm not sure, Timbo. What do you think? Is that a reasonable estimate? Half a meter?
So
I guess when you talk about the depth of the snow, half a meter might be possible. But remember, there's a lot of air in that snow, so half a meter of water seems a little bit on the high side.
So like in the lab we did last session, we did an estimate of how much water we could melt out of a ripe snowpack in the mid latitudes from noon to 1 in the afternoon. And at that kind of peak hour of melt for the day, we got an estimate of 3 millimeters of melt. So I'd say that a half meter of melt would be on the very much on the high side. We tended to see in our point estimate of the reconstruction model a few millimeters, maybe up to 10 millimeters a day at most. But that's, I think maybe talk a little bit about like the degree day. That's maybe one place where people could get these more like empirical estimates of how much melt per day. But I think for the reconstruction we do, the main point is by understanding the energy balance each day, instead of choosing a fixed number of melt, you can actually estimate pretty accurately how much melt actually probably occurred based on the energy that hit the snow that day.
This balance is not equal to all areas. It's different for each area. I mean the melting.
Yes. Yeah, so oh, go ahead, Carl.
Well, at higher elevations, there's less atmosphere that the sun has to move through. So the solar radiation is less attenuated. And at those highest elevations, you could have a stronger melt. As you move down in elevation, there's a lot of scattering going on in the atmosphere, and so there's a bit less solar radiation. And as we saw, the solar radiation is the main driver, especially in areas that aren't forested. So when you have some tree canopy, which is there's some here and there where snow exists. In these regions where you guys work, the solar radiation is attenuated, but the long wave radiation is higher, adding to the melt. So, yeah. I've got a question. So why might the highest elevations have the most SWE in measured depth, but not the most volume?
Yeah, maybe the density of fresh snow is low.
That could definitely contribute. There's another key factor besides density, though, that's worth thinking about. So those mountaintops, they're very
Is
small.
there also
Very steep.
Is
Yeah,
there-
yeah, yeah.
is there
Steepness of the
also
air.
Go ahead, Amrit, and then Shahim, you can go next. Yeah.
Yeah, maybe
okay.
because of the steep terrain, the snow could not accumulate and they slide due to the influence of gravity.
Snow can definitely, from avalanches, and slide downhill. Let's see if somebody else can get what I'm looking for.
Yeah, Shahim, what were you gonna
Take a guess?
Yes, I mean that. Is it also impact of ultraviolet and ice peaks of mountains that cause snow melting?
Yeah. So let me repeat the question. Maybe I should just speak up with the answer. So think of a mountaintop. The mountaintop is very small. So the snow can be deep on those mountaintops, But as you move down the mountain, there's a lot more area at those middle elevations. And so those middle elevations, if they have a moderate amount of depth of snow water equivalent, it's over a much larger area. So often you get the deepest snowpacks at the top of the mountain, but the volume, the main volume of the snowpack is held at moderate elevations because there's only a few peaks and there's a lot of area at the moderate elevation. So that's the answer I was looking for in terms of how much snow water equivalent is there. Yeah, I will agree that at the highest mountain peaks, you can have faster melt rates because of more solar radiation. Does anyone have any questions? I guess, you know, I'm happy to continue to put some questions out there, but please feel free to speak up or write a question in the chat.
Yes, I have a question.
Go ahead.
Yeah, I think you have explained it, but it's not clear for me. In northern provinces of Afghanistan and northeast province of Afghanistan, the snow depth is about 1 to 2 meters. And in the first day lecture, you mentioned we collect the data in AMSR radar. But my question is that the AMSR radar is collecting the data in C-band. And the penetration level of C-band is about 6-7 centimeters. And the snow depth in Afghanistan is 1 to 2 meters. So how to estimate the correct snow equivalent, William? This is one question. And the second question is that if we collect the data in MCR radar, so it's a spatial resolution, is very coarse. But what's your idea if we use the InVSat satellite, InVSat Advanced SAR? It's also launched in 2002 till 2012. It has high resolution, about 5 to 100 centimeter resolution, meter resolution. So what's your idea about if we collect InVSat and also we use the Sentinel-1? Just there may be 2 years gap from 2012 till 2014. This is my 2 questions. If you give me an answer, thank you.
Yeah, so I'll start with the first one. So passive microwave does saturate and can't see the full snow depth. So generally, you're always going to get an underestimate from the passive microwave. We've found, in comparison to the reconstruction, which we validated over large areas and at many points, that the reconstruction shows there's 10 times much volume as we see from the passive microwave, because the reconstruction can go up to as much energy as was melted, where the passive microwave is saturated. So I think that my personal opinion is that passive microwave is most useful for looking at the history. So if you know the last 10 years and you know where this year falls compared to the last 10 years, that's how passive microwave is the most useful. For estimating absolute volumes, it's much less useful unless you have some kind of scaling factor that you can use. So, I showed one slide at the end of my lecture where I, sort of combined the scale of the reconstruction with the passive microwave, but no one's doing that operationally, and that's just an idea. But in context is where the passive microwave is the most useful. Let's see. So you mentioned NVSat. I'm not super familiar with that. Let's come back to that in a second. I think you mentioned Sentinel as well. There's a few Sentinel satellites. Some of them are optical, similar to MODIS, and those can be used. I could maybe for the next lecture put in the differences between some of those. Sentinel 2A and 2B are a higher spatial resolution than MODIS. They're at 20 to 30 meters. whereas MODIS is at 500 meters, but they're not coming over every day. It's every 3 days. So they're a little less frequent, and snow can melt in that time period. I think another one of the Sentinel satellites has passive microwave as well. I'm not super familiar with the sensor.
So I'll jump in there real quick, Carl. So I just posted a link to everyone in the chat that has a reference to the latest paper using Sentinel-1, which is the radar Sentinel satellite. And I'll say the research community is still figuring out the best way to use this higher resolution radar data for SWE mapping. And the one thing, so there's actually a really big effort going on right now called SNOPEX, which is a big intercomparison and validation effort from the snow science community to try and better nail in our uncertainties of these various methods that we use to map snow. And one of the interesting kind of things that'll probably be happening in the next few years is a lot of this passive microwave and radar data, it's really good when the snow's dry, if you're going to use it. Once the snow gets wet, the signal is really difficult to detect and the satellites don't work as well. So the reconstruction works really good in the melt season when the snow is really wet and it's melting and it's clear. And so there's actually potentially a really good combination of measurements between like Sentinel-1, which might give you really good midwinter estimates when the snow's dry, and then reconstruction in the spring when the snow's wet, and you can use that. So I'll say kind of the nuance of getting really, really accurate year-long estimates of snow water equivalent in the mountains everywhere is kind of a current goal of a lot of researchers in trying to figure out kind of the best way to deliver those products. So that paper, that reference should give you some good information on kind of what's available as of now with that Sentinel-1 satellite.
And Sentinel-1 uses active microwave, which we actually didn't go over. I think I had one slide that said, reconstruction, and then it had passive microwave and then active. And so we hadn't really in these lectures gone over active microwave. The NASA satellite that was used actually didn't work the active part. So but SAR, as Timbo noted, is sort of the direction that much of the research is going these days.
Thank you. And I have just one question more. Is there a GUI or graphic user interface application to use instead of Jupyter? For example, in route monitoring, we use GeoClaim and Spirit application for time series analysis. Is there any GUI application instead of Jupyter to use for SWE?
I think the answer is no, that there is no graphical user interface for estimating SWE. It's definitely something we'd like to develop. I think forecasting SWE is a really, or near real-time SWE. There are current estimates of it, but it is really something that is measured at points, and spatially distributed estimates of SWE are challenging. And the methods we're showing you are the ones that we best know with reconstruction, and then we'll be talking more about machine learning, which builds off of the reconstruction in the next lecture. But I don't believe there's any SWE graphical user interfaces for sort of doing this at this time.
Okay, thank you.
Yeah, and I'll say in the lab today and the lab on Wednesday, you'll see we're going to go over some ways that you can visualize SWE in a really usable format for people who make decisions. And right now, when we make those products, we just make them on a research base. We make them when we need them for different things. So that's one potential future opportunity is if you guys see that some of these products would be useful to kind of implement further, there's definitely, that's like another step that could be taken in the future. And so that's, yeah. I see Amrit has his hand up. Do you have a question, Amrit?
Yeah, maybe I just want to add a few things on the paper that you have shared.
Yeah.
So ICIMOD is also part of that work, and we have provided the field-based snow depth measurement for that particular research. And it looks like the product is doing good for the SKS region. And currently I'm also using that product. It provides you the daily snow depth data for about 1 kilometer spatial resolution. So if anyone is interested for any location within the SKS region, then I would be happy to provide that snow depth data set to them. Yeah, that's it. Thank you. Back to you, Timbo.
Awesome.
Some
That's really
local
great.
expertise.
Yeah. So one more thing I want to show while we're waiting for more questions to come in. I just want to share my screen really quick, and I'm going to share the link to another paper. And this is just an example of some of the ways we can use reconstruction, SWE reconstruction, to understand what's going on in the mountains. And so this is a paper that Carl, Ned, and I and our friend Mackenzie just wrote. We published it just a few weeks ago. And what we basically did is we used our reconstruction model to look at basically how clean the snow was in the high mountain Asia this last year compared to the prior 20 years. And if you guys want to browse this, you can look, but basically we have two models that we use to estimate the snow cover and the snow properties. And both of those models showed that while snow cover this last year was about the same as an average year, the snow was significantly cleaner in both of our models during the end of the melt season, presumably because there were more lockdowns and less transportation and kind of less activity going on during the melt season. And so this is just one way that we can see, and you can see up here in this figure, we actually were able to produce an estimate that showed basically how much less water melted all across this region in 2020 than would have if it had been more of a normal year with dirtier snow. So this is one kind of application of the SWE reconstruction methods that we developed that was a kind of a useful result for this current year.
And that informs our future as well. We know that if there's more transportation and more, say, dust storms, that we might get extra melt from that.
Okay, do we have any more questions before we move on to the lab portion of today's exercises? Okay. I am going to copy the link to today's lab into the chat box. So everyone should have gotten the link, and we're going to have everyone load up the lab on your computer, and we're going to start a poll that I want everyone, once they have the lab loaded and ready to go, click yes in the poll. And once we have everyone on the same page, then we will move ahead with the lab for today.
And I'm happy to continue to answer any questions in the chat about the lectures or about the lab during the lab today. So feel free to keep popping stuff in there.
I'm going to go ahead and share my screen right now as my computer is also loading the lab currently.
Looks like we have about a third of folks. So we'll just keep waiting. whoever just joined, sorry I missed your name, but Timbo posted the link in the chat there to my binder. So you can go ahead and click on that to get started for the lab. And please fill out the poll if you have loaded, so we can keep track of how many people. You can just click yes on the poll. We've got about 8 people that said they're loaded. Looks like it's taken a little bit longer for some of us today than it has in the past.
Yeah, sorry, this is taking a while. I don't know why it's so slow today. I'm gonna try reloading mine one more time. Oh, that is the wrong lab. Okay. All right. I am up and running. We have 9 people up and running. So I think what we're going to do while people are waiting for the lab to load, I'm going to start with some of the just talking about the lab. And hopefully by the time we get to the actual code, the rest of the group will be up on the same page.
Hey, Timbo.
Yeah.
I've got just a suggestion. You might want to put that level before in that so people can click on the IPYNB. It seemed to start immediately for you when you did that.
Yeah. So start.
Yeah. Just the link that's back one level.
Yeah. So I'll go back and give everyone the GitHub page that the lab is on. So if you guys go to this GitHub page right here, and then you scroll down. So I'll go to that link too. I'll show you on my page. If you go to the GitHub page link, it'll get to the page that has the lab on it. If you scroll down to the bottom, there'll be a link here that says Launch Binder. If you click on that Launch Binder tab, that should fire the lab up pretty quickly.
And some of you might not see all those files expanded out. You'll just see the launch button pretty close to the top.
And for everyone's reference, this is on this GitHub page, on my GitHub page, I have, you guys, this is all public. You guys can see this whenever you want. There are all 4 of the labs for the training, along with the code that runs the snow mapping and the code that estimates the SWE reconstruction. So this is all accessible for anyone to look at whenever they want. And today we're doing this lab 3, the decision support tools using SWE reconstruction and fractional snow cover analysis. So once it launches, you should be on a page like this. And this is that same page we saw in the last few labs where we basically have all the data that we're going to use in today's lab. And then the Python notebook that has the lab exercise. So I want everyone to click on the Python notebook. And that's going to fire up the lab. And so for today's lab, what we're going to be focusing on, sorry about my computer, just, you guys there still?
Yep.
Can you see my screen?
Yes.
Okay, cool. All right, so for today's lab, what we're going to be looking at is estimates of snow-covered area and then SWE reconstruction from MODIS. And we're going to be looking at a handful of years over Afghanistan and looking in one basin in particular at what we can learn from daily maps of the snow cover and the SWE reconstructions we have in this region. So first, we're going to import all of the necessary Python information that we need for the lab. These are all the packages that we're going to be using. And then kind of to get started, so the main sensor that we're using for this lab is MODIS, which is the Moderate Resolution Imaging Spectrometer. And Carl goes into a lot of details about this satellite in his lectures. And it's really important to kind of first get a sense of, well, where are these data coming from that we're going to be using to map the snow? And so one thing that I really encourage all users of data products to do is, no matter what level you're going to be using it at, to spend a little time to kind of understand where it's coming from, because that's really important to give you a sense of when you can trust it, knowing what went into creating the information products that you use, and getting a better sense of kind of when it works well, some caveats and restrictions, and understanding just kind of overall what you're using, where it came from. And so in today's lab, we're using these SWE products, so looking at the snow water equivalent. And that's quite a few steps removed from the actual data that was collected by the satellite. And so this first little section of the lab is just to give you guys some references that you can use on your own time. And we'll dive into a little bit here just to understand with these optical satellites that are in space, kind of how they collect the data that we're going to be using. So one tool that I really like, that I find really useful as kind of a first overview of a new data product, is this link here for Worldview at NASA. So I'm going to click on that really quick. And what this does is it basically shows a whole bunch of different satellites and products that are available from any day over the whole Earth. And so I find this is a really good way to get a first kind of gut check about what's going on. And so what we're going to do first is we're going to look, and this is for today. So you can see each individual satellite overpass. You can see it's only made it about halfway across Australia so far today. So the next image it takes is going to be over here. And we can look at kind of the data it acquired. Down here on the bottom, we can change the day. So let's go back one day, just so we have data from everywhere. And what I want to do is pull into the area we're interested in, which is high mountain Asia. So you guys can browse around a little more here, but this is just a good tool to get a sense for, this is where the satellite data is coming from. This is the data that we're seeing originally. So can you guys see anything that might be in the way of measuring the snow every day? So do you see the mountains? Do you guys see any mountains that you recognize, any regions that you work in on your Worldview portal on your computer?
Yeah.
Yeah, so you can see the mountains, and you can see also there's a whole bunch of clouds sometimes that are in the way. And when we scroll through the different days, you can see that the clouds move. And another really important thing to notice, especially with MODIS, if we zoom in here, the quality of the image is not the same every day. So here's a day where we have a really clear view of the snowpack. We can see all the snow. We can see some of the clouds. And if we go over one day, this is a really good example. If we zoom in, you can see this is pretty blurry and not so great. But if we go just one day over, the picture is actually quite a bit better. And this has to do with something that Carl talked about in his lecture, which is the view angle of the satellite. And so when we're mapping snow every day from one satellite, we can't always see, the satellite doesn't see everything, everything from directly overhead. So on some days, the satellite is actually looking from the side. And so this is an example of that, where on this day, we can actually see here the edge of the satellite overpass. That's this line right here. So both this region and this region over here are areas where you're at the very edge of the satellite viewing geometry. And so the pixels are really big and really off nadir. And so this is a day where actually each individual pixel is actually about 10 times as large as it is on a day when the satellite is directly overhead, which is a day like, oh, hold on. Like this day, where you can see the image is much crisper because the satellite was directly overhead. So Worldview, I encourage, if you guys want, this is a really good tool to browse around and look. And it can actually give you some insight into what's going on right now, as this is current. It goes all the way up to the current day. So what we're going to do with MODIS, with that MODIS data, is we're going to generate two really important properties of the snow that we use in our SWE reconstruction. And that's both the snow covered area and the snow albedo. And as Carl talked about in detail in his lecture about how we derive those properties with our remote sensing algorithms, and then how we can even correct for those properties when there's trees in the way of the satellite sensor. And so another really important thing about MODIS data, so the reason we like to use MODIS for our products is that it was launched a really long time ago. So the data starts up in the year 2000 and it's continuous until today. And so that means we can use the same sensor to generate estimates every single year. And this is really important because we have continuity across many years for the measurements that we have. So we have a 20-year record, or I guess 21-year record now of snow properties all over the globe. And one interesting thing about MODIS, if you guys were to go and use MODIS data, is that the data comes in this projection that you might not be familiar with. That's the sinusoidal projection. And there's some important properties about this projection. And I give you some information here about it, where basically the projection, each pixel is exactly the same size. So it makes it really nice for doing calculations and computations where we care about how much volume or how much snow cover we have over an area, because we can sum up the pixel volumes and get answers that are correct. Some projections, the pixels aren't the same size everywhere. But because of that, if we look at this really quick, the sinusoidal projection, here's an image of it. It's not exactly what you might see when you look at a map you normally look at. So the data can look a little weird. And so in today's lab, when we plot pictures of the basins we're looking at, you might notice that the basin doesn't look how you're used to seeing on a map. And that's because the data are in this sinusoidal projection, which is how all the MODIS data are stored. Another important thing about MODIS is that it's on 2 satellites. So MODIS is the name of the sensor that collects the data. So it's the sensor that's taking the pictures, and it's on 2 different satellites. So one of the satellites is named Terra, and the other satellite is named Aqua. And here are 2 links to the data for both of those satellites. And there's a lot of information on these pages that goes into detail about all the data that's collected from both of them. The main thing to know for snow mapping is Terra takes a picture in the morning, so around 10:30 a.m., and Aqua takes a picture in the afternoon, about 1:30 p.m. Also, Aqua, the afternoon satellite, some of the sensors broke right after it launched. And so it's actually not that great for snow mapping. There have been some corrections that people have developed to kind of make it a little better, but because it doesn't work as well as Terra does, and because it takes pictures in the afternoon, when there tend to be more clouds in the mountains, especially because of convection, we choose to use the Terra satellite data, MODIS data, for all of our work, because there's less cloud cover in the morning and the data quality is higher. So our recommendation for users of snow data, if you're going to use the MODIS data sets to derive snow cover maps, we highly encourage you to use the Terra satellite and the morning acquisitions. And there's a bunch more information about MODIS here in these links. And for this lab, what we're doing is that we're going to be using snow cover and snow water equivalent from this MODIS on the Terra satellite from 2003 to 2011. I've prepared some data packages over Afghanistan, and we're going to look at the SWE and the snow covered area. So before we go and start looking at that data, does anybody have any general questions about MODIS or optical satellites before we move into looking at the data?
Hello, Timo. I have one query.
Yeah, go ahead.
Yeah, most of the time I have seen that you, Carl, and your group like McKinsey, they mostly use snow cover data from MODIS 09A1.
Yep.
And the standard NSIDC product is MODIS 10A1. So can you highlight some of the difference between these products? As far as I know, MODIS 09 is based on the reflectance using some linear on mixing model. So I guess some information on this would be useful for all of us. Thank you.
Thanks for that question, Amrit. That's a really, really good question. And I think, do you want to take it, Carl? Do you want me to take it? Oh, you're muted.
All right, I'll take that, Timbo.
Okay.
Thanks. Yeah, so MOD 10A1 is available globally at the National Snow and Ice Data Center. And that product, what it does is it takes one band in the visible, which is very bright, as we've seen from the spectral albedo plots, and one band of a longer wavelength in the shortwave infrared, which is dark. And it does a difference between those two bands and then divides by the sum of them to normalize it. So the MOD 10A1 product, the algorithm was originally developed in the 1980s. And it's very good at mapping snow where snow covers the whole pixel and there's not much forest. There was a little bit of confusion about what we do. So the MOD 10A1 uses two reflectance bands. What we do is we take Mod 09GA, which is the surface reflectance, and we use, I think it's, I'm sorry if it's either 6 or 7 of those bands. Seven bands. And we do spectral mixture analysis. So I showed this equation that has different N members, and the product we're using is from Mod SCAG. It's the MODIS snow cover and area grain size. And the input to the MODIS snow covered area and grain size algorithm is Mod 09GA, the surface reflectance. And one advantage is we get the grain size, which we can convert to albedo. Whereas the Mod 10A1 algorithm, they use a separate algorithm to look at snow albedo. I've actually done some, I don't think I included it in our lectures, but when I look at that, they don't account for, say, the off-nadir viewing. So I've seen the albedo jump from 0.4 to 0.95 to 0.4 to 0.95 on successive days because of the off-nadir viewing that Timbo was just showing you. Since we take into account the off-nadir viewing by weighting the observations based on the view angle of the satellite, are able to sort of deal with that issue of the off-nadir viewing effect on the snow albedo as well. So Mod 10A1 is global and available everywhere. It's at the National Snow and Ice Data Center. Mod SCAG is a bit more hidden. The Jet Propulsion Laboratory currently produces that. We're working on expanding the access, and right now we are running the Indus River Basin and on snow today at NSIDC in near real time. So there is some opportunity for you guys to use that product, and I can try to add that to the next slide or the next lecture as well.
And I'd say, yeah, to piggyback on what Carl just said, one of the benefits of Mod SCAG and us using the surface reflectance data and using the physical model to derive the snow cover and the snow properties is that we generate an estimate of the fraction of the pixel that's covered by snow. And our estimate of snow albedo is also specific to that snow fraction within the pixel. So a lot of the standard albedo products from MODIS through NASA, they do not take that extra step to try and determine the albedo of the snow within the pixel. They generate a whole pixel albedo, which when you're interested in how much snow is melting and how much snow melted over the entire season can lead to gross errors in your estimates. So that's one of the kind of most important reasons we feel our product is really useful in the mountains for water supply forecasting. Many of the methods that map snow cover end up with a pretty similar estimate of snow cover. So figuring out how much area is covered by snow is an easier challenge. Figuring out how dirty the snow is, how big the grain size is, how reflective the snow is, and also for a satellite where the pixel is really big, figuring out how to do that in a way that accounts for all those issues, that's really challenging. And that's where we've put a lot of time in our work into getting that snow reflectance correct. And Carl can give if you want to share your screen again, Carl, do you want to talk about that for 1 sec before we move on?
Sure. Do we have time?
Yeah, we got time.
Okay. Can you see the slide here now, Timbo?
Yeah.
So the graph on the left is just to remind you that solar radiation and reflected solar radiation drive the energy balance. But here's an example of 4 different dates showing in the upper left is a false color image. So the soil looks red, clouds look white, they're a bit mixed with the snow that looks a light blue color. So I have this labeled as proposed snow albedo. That is the product that we are creating. Down here, you have the mod 10A1 snow albedo. You can see in this particular case, some clouds. It's not estimated in some places. There's another product called MCD 43, but that's whole pixel albedo as well. So what you'll notice is that the values in the proposed or our product are about 0.8, and that's reasonable for a snow cover to have a 0.8 albedo. You can see in the mod 10A1 that there's a lot of values down here at like 0.5, as well as the MCD 43, and that's exactly what Timbo is just describing, where it's using the reflectance from the entire pixel, not just the snow portion. So, a main advantage is sort of that. You can see our product is also spatially and temporally complete. There's a lot of missing data here in white, either where there's no snow or where they didn't estimate an answer. But if you look at this mod 10A1 here on the 5th, and then you look the next day on the 6th, you can see that now the snow albedo is up at 0.9 at some of these elevations. And then on the 7th, it's back down to 0.4. And then on the 8th, it's back up to 0.9. And this is just unrealistic. The snow albedo, it could change that much over a few days of melt or if there's a big storm, but it's very unlikely to be bouncing back and forth between those values. You can see both the MCD product and our proposed snow albedo are much more consistent over time. But again, the MCD 43 is the whole pixel albedo. Timbo, you can take it from there.
Okay, thanks, Carl. So I'm going to share the lab again. And that's kind of one of the main takeaways I'd say from the lab today for users of snow data is for water supply management and for understanding the snowpack, you really need good data on the snow cover and the snow albedo. And snow albedo doesn't get as much attention as snow cover. And it's actually pretty difficult to measure it that accurately. Okay, so back to the lab. Now what we're going to do is we're going to look at snow cover and melt for our region in Afghanistan. So let's run. Oh, let's go back and start this again. So it looks like this is running. Let's see. Okay. So, and if you had an error in your lab right now, you might have to restart the kernel. We talked about that yesterday, but up here is this kernel button. If your lab stays inactive or you don't click on anything for a few minutes, it'll die. And so you have to do the restart button up here. So here's a picture of Afghanistan, and in purple here is this basin that we're going to be looking at today for both the SWE and the snow cover analysis in. And so one thing, just kind of, there's some details here I'm going to kind of browse over that you can look at more closely on your own time. But one of the things that we use a lot in our work when we're looking at snow cover and SWE is these masks of the basins. And so what I'm just showing here next is what this mask looks like. And so if you guys are doing coding, computer coding in Python or R or MATLAB or whatever, logical masks are a really powerful tool to select specific areas that you care about to get answers from. And so what I wanted to show here is basically this is the image that we're going to be using for our entire lab. And what we can do is while we have data points in the entire image, we really care about what's going on within our basin. And so what a logical mask does is we can see that in this image, there's just two values. There's values of 1 and values of 0. And the 1 values, which are in yellow, are all the pixels that we care about what the estimates of the snow are. Those are all the pixels within the basin. And so we're going to use this logical mask, which we call the basin mask, in a lot of the code down below, to select all those MODIS pixels that are taking a picture of our basin of interest. And we can use that to do really cool analyses, like calculate how much water is in the entire basin each year. Okay, and so the other thing that we talked about a little bit is this fractional snow cover. So I'm going to talk for a second about that. We talk a lot about snow cover percent, fractional snow cover, spectral unmixing, using the MODIS satellite to map snow. And it's really important to understand that the snow on the ground varies at a much finer spatial resolution than the size of the pixels in the satellite. And this is a really important point in the mountains. I have a link here to this paper. If you guys click on it, there's two figures, figure 6 and figure 7, that kind of show this. And this is a paper that looks at how, so if we pull up the PDF, pull up the text, this is a free paper too, you guys should all be able to access it. And if we scroll down to the figure 6 and 7, we'll look at this one, we can basically see here's some really high resolution pictures of snow cover in the mountains. And then here's the areas that are snow and snow free on different dates. And you can see that each of these boxes is the size about of a MODIS pixel. And you can see even for one spot, 1 year on different dates, the amount of snow cover within an individual pixel is really different. And so this is a really key reason to need the fractional snow cover maps, where what we're going to be doing in the lab is our pictures are each of these gray boxes, that's 1 pixel. And we're figuring out, well, what percentage of that pixel is covered in snow for all of the pixels in the image. And so this is kind of just showing you why we care about that fractional cover of the snowpack, because the snow is really dynamic, it changes a lot, and it varies at a much higher spatial resolution than the satellite. For our research, we only use images that are at ½ meter resolution as maps where we can consider the pixels are either entirely snow covered or not snow covered. Any spatial scale larger than that, and we assume that there is some mixture of snow and other surfaces in the pixels. Okay, so back at the lab, what we're going to do is we're going to look at maps of snow cover. So in this lab, I'll go here to the data. You'll see in the data section, we have all these FSCA data products, and these are geotiffs that I've put together of Carl's MOD-SCAG product over Afghanistan for these 11 years. So these are daily maps of snow cover for each of these years over this region in Afghanistan that we're doing the lab within. So what we're going to do first is we're just going to load 1 year of data from 2011. And we're using what's called raster.io is the package in Python to do that. And just to give everyone a little background, we have the year that we're doing it. This is the name of the file. For this Python package, we have to open the file first. So that's this src variable. And then once we've opened the file, we actually read in the data from the file to a variable. So it's a 2-step process. So that's why you see these 2 steps here. And then what I'm doing here is I'm just printing how big is our image, how big is this geotiff from 2011. And when we print that out, we can see that we end up with a data cube that is 365 by 196 by 169. And so that's the size of it. So the 365, there's 365 bands of data in the geotiff. Each band of data is 1 day in the calendar year. And then we have an image that is 169 pixels by 196 pixels wide. So let's actually look at a day of data now. So one important thing I want you guys to think about today in the class is for a lot of these visualizations, the end goal is for users who make decisions to get these data products and have them be informative for their needs. And a big part of making data informative is how you visualize the data. So there's many ways you could display exactly the same information, but some ways are far more effective than other. And so I have 2 links here in this section. So the first is just kind of the available ways within what's called matplotlib, which is the plotting library we're using for this lab. And these are the ways, these are all the color maps that are available for us. And down here, we can see all these various color maps that are available to use. So if you guys want to look at that for a second, think about what are the categories of color maps? Why would you need different color maps? And what do you guys think potentially a good one would be for mapping snow cover?
So what are the, you asked Timbo, what are the six types? Is there 6
Yeah.
types?
There's 6 types.
Okay.
They're kind of labeled here. So basically we have color maps that are sequential. So they change proportion from one color to another color. A really important thing with these color maps, a lot of these color maps that change from, like, let's say, annotate, a light orange color to a dark orange color, or a green to a blue. A lot of these color maps were not created to do science with. And a lot of people use these default color maps to display scientific data. And a problem with that is that it's not consistent, the change in color from value to value across the color map. And that's where these ones come in up here that are really useful for science. These are called perceptually uniform sequential color maps. And this is where each value in the color map changes exactly the same amount as all the other values. So when you look at it visually and you see a dark blue or a light blue in different images, you kind of have an idea of, okay, that's exactly this, that is the right amount of distance apart from the other ones. So that's a really important point for color maps. Another one is that you get also these kinds that are called diverging color maps, where you basically start with a white color in the middle and then you diverge to two different colors where you're trying to show differences between things. There's color maps where the color actually comes back around at the other side. And then the last kind that's kind of important are these qualitative color maps. For qualitative color maps, you could think of like a map of different countries. Each country is just a different object, and you might want a different type of color map. For a lot of scientific data, you're probably going to be most interested in qualitative color maps, diverging color maps, and perceptually uniform sequential color maps. And one more thing to point out here, this tool here, colorbrewer2.org. I find this really useful if you're interested in trying to find for your data. Let's say you get data from someone and you want to display it in a useful way. You can give them direction on how to color it. Or if you're a data producer and you want to produce your data in a way that is useful to end users, I find this as a really useful tool. You can browse it on your own time for finding different color maps that work well for your data. Because there's lots of things you might need to consider. You might need it to be printed in black and white on a piece of paper. Not all color maps work for that. You might have people who are colorblind who need to look at your map. Not all color maps work for that. Depending on the number of data classes you have, the type of data, here there's three main types, sequential, diverging, and quantitative. You want to color your data differently. So those are just some resources for all the participants for when you're making maps in the future. They can really help make a big difference in telling the story with your data. So what we're going to do now is we're going to make some maps of snow cover and SWE reconstruction. And when we make them, we're going to try and choose color maps that really help us see what's happening with the data. So the first thing we're going to do is we're going to pick a day to visualize snow cover. And so we're going to use the 11th day of the year right here. And I'm going to use this map called the blues color map. And you're going to see what that looks like here in a sec. So we're going to set the color map. I actually want to use the colors in the opposite order that they come in the default, so I can actually reverse the color map colors, which we're going to do right here. And another thing too is we're only interested in the values within our basin. So we don't want to assign values from our color map to the pixels outside of our basin mask. So I can actually use this command right here to set all of those pixels to a totally different color that's not going to get in the way of us understanding what happens with the data. And now that we've done this, we can plot our map of the snow cover. And when we do that, this is what we end up for the 11th day of the year in 2011 for our basin in Afghanistan. And you can see we both have data on snow cover and we visualized it in a way that's informative and useful, where white pixels represent pixels that are fully covered in snow. And as those colors transition to a dark blue, we get to pixels that have no snow cover. And then separate from those pixels, all of the pixels outside of the basin we've colored gray, so it's not to confuse us or get in the way. And so here we have from ModScag, which is Carl's product, this is a map of snow cover of the basin in Afghanistan. And this is really cool. This is quite high resolution compared to the products we were looking at in Lab 1. In Lab 1, if you remember, each pixel was about 30 kilometers by 30 kilometers. There were only about 8 or 9 pixels over this whole basin. And now you can see we have hundreds and hundreds of pixels because our pixel size is much smaller with the optical satellite. So with MODIS, we get pixels that are about 463 meters by 463 meters. We have a much better understanding of the spatial distribution of snow cover in the basin. Does anybody have any questions at this point about this first snow cover map or what we've done so far before I continue on? Okay. So now what we're going to do is we're going to go and we're going to look, okay, this was one day looking at all the pixels. Another useful thing is to pick a point. And when we pick a point, we want to look for every day of the year, what's going on. So we're going to plot a time series for one pixel for 1 year right now. So for that, what we're going to do is we're going to take this FSCA variable where we loaded up the full year of SWE data, and we're going to pick one point and we're going to plot it. And here we have that. So this is of that GeoTIFF we had, where we had 365 bands of data. We've taken 1 point from each of those bands and we can plot the snow cover fraction of that pixel through time. And you can see, because we have this as a calendar year right now, we can see kind of what we would expect. So in January and February, we have a lot of snow cover over that pixel. In the spring melt season, the snow cover slowly decreases. There's a wide period in the summer with no snow cover, and then the snow cover picks back up again in the winter. And so this is kind of useful, but this is just one pixel in the basin. So that was one of these pixels. What if we want to actually look at, well, over this whole basin, how is the snow cover changing each day? And this is really useful because with the optical satellites like MODIS, we can actually measure this every day with pretty high resolution and accuracy. So while snow cover doesn't tell us the SWE directly, it is a really useful tool that we have available to us in near real time that we're very confident in. So what we're going to do now is we're going to do that. So I've written this function here where we take in our data cube and we can actually go through and we can sum up and sum the total fraction of snow cover in the whole basin. And so when I run this function, the output we can see here is that we end up with just 365 values. And so we've compressed each of these images up here, each of these daily images into one value of the total fractional cover of snow in the basin. So let's plot it, see what it looks like. So here we go. So this is looking across the whole basin, how much snow cover we have. And so here you can see that in 2011, it looks like the snow actually came late. So it was pretty dry at the start of January. There wasn't much snow cover in the basin. We had one storm here at least. We had another storm a few weeks later. We see the snow cover held steady in the basin at over 80%. And then later in the year, we see the snow cover rapidly dropping as the melt season progresses. And then we can see that in the following year, in 2011, the same year, but in the fall, the snow cover kind of slowly building back up again. So this is for 1 year, that's pretty cool. We can also look at this for every year. So what we're gonna do now is we're gonna do that same plot, but we're gonna run it for all the years of our data. Oh.
It's worth saying that Timbo's plotting the basin-wide snow cover percent, so it's an average. Is that right, Timbo? Where
yes,
what you would do is you would need to multiply that by the area of the basin, and then you would get the total snow-covered area. So these are fairly interchangeable. The plot would look the same, but it would just have a slightly different number on the y-axis.
yeah. Okay. And this type of plot, one thing that people call them is spaghetti plots, because it kind of looks like a bunch of pasta, because you're overlaying for the same time period every year over and over again. So one thing though you can see here is we're looking at the calendar year because the data was provided in a calendar year format. And this isn't as useful as it could be because we're kind of seeing the start of the picture partway through the year, and then we're getting some information from the following year over here. So for a lot of our water supply work with snow, we actually like to look at the water year instead. So what we can do now with with this code down here is we're going to take the same data set and we're going to reshape it so that the data is by water year as opposed to by calendar year. So we'll do that next. We'll run. And what we're going to do is we're going to take all the data from the correct years, place it into a single water year, and then we're going to plot that. And here we go. And you can see these basin-wide snow cover graphs look pretty similar to the SWE graphs that we saw in Lab 1. Where you can see that in the start of the water year, in September, in October, November, December, the snow accumulates and then it melts out. But there is some variability from year to year, especially when the first storm comes for when that starts. So now that we looked at this with snow cover, we can start to think, well, how could we use snow cover to help us make decisions, or how could snow cover help us with SWE? And so now what we're going to do is show some ways we could visualize snow cover each year that can help with that kind of information. And this is playing off of what Carl talked about, some of his work with Snow Today, where Carl does a lot of these graphs in near real time over all of America right now. And he's working on getting it running in the future, potentially over high mountain Asia. And we're going to show kind of some of the ways you can visualize snow cover in near real time. So one kind of useful tool is to actually look at the number of days that each individual pixel is covered in snow. And this is actually quite variable. And this is just looking at, for a year, for a water year, how many days of that water year up to a certain point was the pixel covered in snow. So what we can do is we can pick a year to try this with. So we're going to try the year 2004. And we're taking data from the end of 2004 and the start of 2005. We're loading it up and we're putting it into one variable that shows the water year for FSCA. And now what we want to do to do snow cover days analysis, instead of looking at the fractional snow cover, we only care about when there's snow in the pixel or not. So we're going to use, what you're going to see here is maps like this, which look a little different than the fractional snow cover maps. So this is a map where we've just identified on this day which pixels in the basin are covered in snow. And if we do this every day, we can then add up how many days were each pixel covered in snow. And this kind of shows you too why fractional snow cover is a much more useful tool. So if you look at the amount of information in this map for a single day, and we compare it up here to this fractional snow cover map, this kind of also shows you why fractional snow cover is really useful if you're interested in kind of the spatial distribution of the snow. But one useful thing we can use these binary snow maps for is figuring out how many days over the year was that pixel covered in snow. So now what we're going to do is we're going to do that. We're going to plot these snow covered days map. So what we want to do is we want to pick a day where we care about how many snow covered days we've had so far is. So you guys can change this around in years, where I've set it up where you can pick a month and you can pick a day of the month. And from that, we can figure out which day of the water year that is. So if we're interested on April 25th, how many snow covered days have we had on all the pixels in the watershed? We are interested also, that's the same as saying the water year day number 207. So now what I'm going to do is plot that. And what we have here is a picture of that. So now what we've done is we've taken these daily maps of fractional snow cover. We've identified each day which pixels are covered in snow. And then for the 2004 water year, we have decided that, okay, on April 25th in 2005, how many days was each pixel covered in snow? And that's what this picture is showing here, that in the highest elevations, snow was covering the pixels for upwards of 200 days. And then down at the lower elevations for far fewer days, down into maybe 20 days or 0 days. And Carl's going to talk in more detail, give some examples of where he displays all this data on the Snow Today website and some other ways where we use this operationally. So this is useful, but what's really useful with snow covered days is we can compare the current year to all of our knowledge from all the past years. So like I said, MODIS has been up for 20 years. So we have 20 years of maps of snow cover for all the areas of the earth with snow. And so from that, what we can do is we can figure out, well, on average, how often are all these areas covered in snow? And then we can say, okay, well, in the current year, on today, how does it look today compared to our average expectations of snow cover for the basin? So next what we're going to do is I'm going to make a map that shows that average. And then once we have the map of the average and the map of the current year, we can look at the difference between the two to get a sense of how different the current year might be from other years. And I see Amrit, do you have a question? Do you want to say something really quick?
Hello, Timbo, can you hear me?
Yes.
Yeah, I just have a small query on how you convert the snow cover percentage into a binary snow cover map. Have you used some threshold while doing so, or how you convert that into snow cover days?
Yeah, so I will show you. It's up here in the code. So I did this logical mask here, where basically we just say it's snow covered if the fractional snow cover is greater than 0. One thing I'll say about if there's like a lower threshold, so the ModScag snow cover product that Carl described that we're using, our fractional snow cover product already has a lower threshold set in it. I believe it's 15%, right, Carl?
The raw input that we get from JPL from the ModScag algorithm uses 15%, but we interpolate all the way to 0%. So all of the gap filled products that we have have values from 0 to 100%.
Okay.
Sometimes we choose to ignore the lower values, 0 to 5%, or maybe a few more, because it can be a bit noisy there. If you have some bright soils or some water sometimes.
Yeah.
Yeah.
Cool. So yeah, I'd say in general, we trust the values that are above 5% snow cover. And in this lab, we're just taking all of them and we're just identifying which pixels are covered in snow on every day. So this variable here, water year FSCA, this is a 3-dimensional cube. So it's the size of the image, and then there's 365 layers in it. So by doing this one simple logical query, we can actually, it does it across the entire data cube. So this snow cover here is a data cube that is 365 by 196 by 169 data points large. And it's a bunch of zeros and ones. And once we have that down here, all we need to do to get this map of number of snow covered days is we do this thing right here. It's this count non-zero command in NumPy. And this would be in any programming language, you would basically index your binary data cube of when you had snow cover across from the first day to the day you're interested in, across the whole image. And then this count non-zero basically sums all those up. So you add them all together. And by adding them up, you end up with an estimate of, you get a count of the snow covered days. And that's what we get right here. Okay, so now going on looking at the mean, what we're gonna do is, let's see, where's my, okay. So to get the mean on this day, what I wanna do is I wanna say across all the years in our record, on average, on the 25th of April, how many snow covered days have we experienced so far across all these pixels? So to do this, what I'm gonna do is I'm gonna create this empty array that we have 7 years of data right now we're working with. So that's the 7 here. And then this 196 by 169, that's the size of the image. We're basically gonna create this empty array that we can then fill with our calculations we make each year. This is a really common way to loop through data and fill up estimates that you get. So if we run that, what we're now gonna do is we're gonna run this function down here, which goes through each year, each water year we have data for. It pulls together all the FSCA data. Once we've pulled all the FSCA data together, we run this snow cover calculation. And then we figure out the day that we're interested in the water year. And we then do this count non-zero NumPy command, where we take basically for each individual year, we add up how many snow-covered days we had on every pixel. Once we have that for each individual year, we then fill that into that initiated matrix that we had at the start. And we fill that out with all the data. So let's run this and see what happens. So here we can see, here's the empty one. It's 7 by 196 by 169. When we run this command, still running. This little asterisk here means it's running. I think I mentioned that in the past lab. Oh, and once it changes to a number, that means that it's finished. So we can see our data has stayed the same shape, but now it's filled. So now what we're going to do is let's plot this. Let's look at basically what does a year look like compared from any of these years. So here I see we can pick a year to plot. So you can pick any number between 0 and 6 and put it in here and we'll get different plots. So let's look at the first year. So in 2004, this is what the snow-covered days look like. If we go to another year, let's put, say, 6 in. We can see that graph changes. And so this is all the individual years. This is basically us looking at every year, what it looks like, whereas up here, we just did it for a single year. So now what we're going to do is we're going to compare this to the mean. So for the mean, we're just going to average for each of these years the snow-covered days for each pixel. And from that, we can see here, we have the mean number of snow-covered days. Once we have that mean number of snow-covered days, now what we want to do is we want to compare an individual year to this mean year. And so quick question for everyone. What do you think would be a good color map for us to use to visualize this comparison? If we want to compare the difference between a year and the average, if we go back and look at these types of color maps, who can think of a good type of color map to use to display this data? What do you think? What do you think you would use, Carl? What type of color map?
Well, it looks like we have some students who are getting.
Oh, there we go.
Yep. So diverging, is that?
Diverging. Yep. So we got a few people who said a diverging color map would be a good choice. And that's correct. That is a great choice of the type of color map where we're interested in how different from the average each pixel is, where you might have some pixels where there's more snow-covered days than the average and other pixels where there's less. So we're going to use this diverging color map right here in our plots. This PIYG is what it's called, where we have a lot of pinks and then a lot of greens. Because there's two different colors with white in the middle, it's really easy to visually see areas where there's more or less snow-covered days. So let's do that. Go back to the lab. And you can see here what we're going to do is we're going to compare the difference, where we're going to take 1 year of snow-covered days, and we're going to subtract the average number of snow-covered days from it. We're then going to mask out the pixels that are outside of the basin, and then we're going to set this color map, and we're going to plot it up. So here we go. Now we have a map that's starting to show us some really useful information, where we can look for this year, we can look at how different the number of snow-covered days were compared to the average. And we can see in this graph that at a lot of the higher elevations down here in the south, there were actually more snow-covered days than the average. Whereas down at these lower elevations, there were actually significantly less snow-covered days. And I'll say in general for snow-covered days analysis, we like to look at kind of these higher elevation areas and the mid elevations, which as Carl mentioned, the areas where most of the snow is, most of the water in the snow is kind of these mid elevations. A lot of these lower valley floor areas, especially in this basin, don't see a lot of snow-covered days in general. And so we're more interested in the patterns kind of up here in the mountains. So this chunk, oh, go ahead, Carl, do you want to say something?
Oh, well, I would just say that, sometimes you can have anomalous, snowstorms that, if they do cover lower areas, that can end up being a significant volume. And those are often maybe the more dangerous snows too, because they melt faster or rain can happen on those, creating flooding. So in terms of generally understanding the snow water equivalent, not usually as useful, but with a larger area, they can end up having significant snow, but often it's ephemeral. It snows there and then it's gone.
Thanks. Does anybody else have any questions about snow cover day analysis and snow cover day mapping? Or fractional snow cover maps? Carl's going to show some examples in the next lecture of how we use this on his website. Should we throw the link for your website in right now, just so if they want to look at it themselves, they can? But basically, Carl's operationalized these types of maps with the ModSCAG product for some parts of the world. Oh yeah, Amrit, you had a question?
Yeah, I just like to know more about the difference between snow cover days, snow cover duration, snow persistency. Sometimes people use these terms interchangeably, so it would be nice if you can provide your experience with these terms.
Yeah, so for this lab, there's no persistence filter in the calculation of snow covered days. So we're just adding them all up for each pixel. So there could have been a break where the snow melted and came back again. But that's a good point. For some of it, sometimes you're actually interested in the consistent cover of snow. So at what day did the snow cover start? How long was it before it ended? And Carl, do you have any insight into how you prefer to look at those two different types of methods for mapping snow duration?
I think Amrit's point was a little different in that, like, people call snow cover days and snow cover duration the same thing.
Got it.
So they're really equal to each other. The duration of the snow cover, you know, I would say that they're interchangeable. People call, you know, snow cover extent the same as snow cover. And so there are a few terms like this that are interchangeable. I'm not sure why we chose snow cover days instead of snow cover duration, but the same thing. And I think you mentioned the third one, but I've forgotten it already. Snow persistence. I think that's a little less clear on what it means. Snow can persist around later in the season, but maybe it wasn't there earlier, but it's probably often used as a synonym as well.
Thanks. And then this is the link that Carl put in the chat box that shows this fractional snow cover and snow covered area and snow covered days analysis that is operationalized right now over the Western US. And so this shows how we actually have developed pipelines that can leverage this MODIS data and produce these useful tools in near real time. And you can see that there's a lot of information here that can actually help with water supply management, where even by just knowing the number of snow covered days or kind of how much area is covered in snow, you get some of the same kind of differences in like wet years and dry years that you would get from snow water equivalent. It's not the same as the volume of water in the snow, but it can give you some insights into what's going on. And it's like I said, we talk about all these products have different caveats and constraints. And I'd say these products that show you the cover of snow and the duration of snow cover are the most accurate in real time of anything we have available so far. So now we're going to go on and look at SWE reconstruction with these same data sets. So Carl mentioned in the lecture how we use the snow cover and the albedo of the snow along with radiative forcing data to estimate the SWE reconstruction. And what we're going to do now is we're going to look at some maps of SWE reconstruction and see how we can use that output to really understand what's going on with the snow in the mountains each year. And I just want to say as a note, so to get for the labs to run here on Binder on the internet really quickly for everyone, I converted all of the SWE into centimeters. So you'll notice all the SWE data is in centimeters and not in millimeters. And that was to pack all the data in to make it really quick and accessible for everyone. Okay, so first what we're going to do is we're going to look at maps of snow water equivalent. So we're going to do the same thing. So back here on our page of data for the lab, we have all these geotiffs of the snow water equivalent estimate out of Parball from 2003 through 2011. So we're going to be loading up these geotiffs of Parball estimates to look at our lab. And I just want to mention too, while we're doing this, Carl's been doing a really good job in the chat of answering a bunch of people's questions and posting links to lots of really useful papers. So feel free to look in the chat too if you have some questions. There's a chance that Carl's been actively answering them for you. So let's look at 2011 first. We're going to load up this SWE reconstruction from 2011 with the same way we loaded the fractional snow cover data, where we basically open up the file, and then once the file is opened as the source variable, we can then load the SWE in. And we can see we have a data set that's the same size as the snow cover data set, where we have 365 days of data across this image. It's just with this data set, instead of snow cover, each pixel gives information on the depth of snow and that depth of water in that pixel that's in the snow. So let's look at 1 day of data. So let's pick a day to look at SWE. So we're going to look at the 100th day of the year. And we're going to look at the color map that shows us the SWE. And we're going to use one of those maps I talked about, this perceptually uniform color map, where the difference in value between each amount is uniform, which is really useful for this type of scientific data set. And we're also going to do the same thing where we set the values that are outside of the basin to gray so that they don't interfere with our visualization. So let's look at what the snow water equivalent looks like. And here we go. So here is our snow water equivalent in the basin. We can see we have a lot of variability where we can see a lot more snow water equivalent up in the mountains down here in the south, and then a lot less snow water equivalent in the lower areas, and then kind of up here in the north. And I'll say you can see that there's a lot of areas grayed out here within the basin. And these are pixels where we do not have an estimate from reconstruction at this time, most likely because there's no snow there at the moment. And so we only produce this for areas where there's snow. So now what we can do is we can look and see what this looks like. And so this is taking 1 point out of our map and plotting it and looking through time. What is the SWE in 1 pixel? And here's our graph that shows that, where we have the day of the year and we have the snow water equivalent in the pixel. And so this here we have about 0.5 meter of water in the snow in this pixel. And you can see that we see this nice curve of the snow melting out. We can see how the snow melts out in the spring. You'll see, why do you guys think this line is so flat and perfectly flat here in the beginning of the year? This has to go back to the fact that Carl mentioned where SWE reconstruction only works during the melt season. We can't reconstruct SWE past the peak volume of snow and water in the snow. So in this data product, we basically just extend our estimate backwards at that peak value in time. So we really trust the SWE reconstruction, and we really advise people to use it kind of during this period here, from peak SWE to melt. That's the period of time we're really interested in with this reconstruction product. And this varies from year to year. It's not always the peak at the same time each year. That's just a good thing to remember about SWE reconstructions. So another thing that's really useful is especially for water supply management, we probably don't care about how much water is in 1 pixel in our image. What we probably really care about is in this entire basin, how much water is stored in the snow on any one day, because that's a more useful bit of information. So what we can do is we can actually do that, where we can compute here. I've written a function that takes the SWE reconstruction data, and it actually computes what's the volume of snow in the basin on that day. And what it does that by computing each individual pixel's snow volume. And this is the equation right here for how we can do that, where we have the snow water equivalent for each pixel. which is the depth of water in the snow if it was all melted in that pixel. And we assume that that depth of water extends across the entire pixel. So if we take that depth and we multiply it by an area, we get a volume. So the depth is here. We're going to convert it to kilometers because the basin is so large. A good unit of measurement is cubic kilometers. That puts it in a good kind of frame of mind for how much water is there. And then we're going to multiply it by the size in kilometers of each MODIS pixel. The MODIS pixels are 463 meters by 463 meters. So we're going to multiply it by 0.463 by 0.463. And that gives us the volume in each pixel. And then because we've already masked out with that basin mask I showed you earlier, we've already masked out all the pixels that aren't in the basin. It really is now just as simple as summing up all of these individual pixel volumes, and we end up with the basin-wide volume. So let's run this. And now you can see here, we've condensed our image cube down into 365 estimates or calculations of the total volume of water in the basin every day. So let's look at it. Let's see what it looks like. So let's run this next one. And here we go. So this is a plot for 2011 for this basin in Afghanistan of on each day of the year, the total volume of water that we estimate was in the snowpack across the whole basin. So we can see at peak SWE, there was about half a cubic kilometer of snow of water in the snow. And then we can see it melting out through the year and the final meltout occurring around the 180th day of the year. This is really cool. This is really powerful. These graphs of SWE reconstruction, especially in areas where we have little cloud cover during the melt season, we have a really distinct accumulation season followed by a distinct melt season. These reconstruction plots are probably the best available estimate of how much water was in the snowpack each year in the mountains. With the caveat that, as we said before, the day that you can make this product, show you really quick. This is really important. This is the day you make it. So the day you can make this graph is the last day of the graph. So you can't make this graph at the beginning of the year. So what we're going to do is in the next lab, we're going to show you how you can use some machine learning tools to leverage this information from past years to estimate the current year's volume. But we're also going to show you how, even if you can't make this graph in near real time, we have them for all the past years. So MODIS has been up for 20 years. We have 20 years of measurements of how much water was in the snowpack every place, every melt season. And from that, we can get really good information about the differences between past years. And one valuable tool is using historical knowledge where, like, if there's a year in the past that you remember what it was like, if it was a wet year or a dry year, how the water system functioned, what people needed. And then the current year, if we can see, oh, the snow cover this year looks really similar, people's knowledge of what's happened seems pretty similar, we can then contextualize the current year inside of prior year's experience. And Carl's going to show you guys some examples of this from a past project where we've taken our snow products and we use this tool in a way that we take prior year's SWE reconstructions and knowledge of what happened and use that to help inform what's happening in the current year. Because like we said, this graph itself isn't available in real time. So now what I want to do, so like I said, that where the power comes in, this was 1 year, but this is what we can do is if we run this next chunk, this is where the real value starts to come in. So here I've run for 9 years, the SWE reconstruction for the same basin. And now you can start to see some really big differences. So each of these gray lines is a different year doing SWE reconstruction in this basin in Afghanistan. And we can see that there's a lot of different types of years here. So we see here's three drought years where we start out at about the same volume of water and the SWE depletion curves are all kind of happening at the same time. We then have a few kind of medium-sized years that are still pretty varied. These 3 years are pretty similar too, where we all start with about the same amount of water. But then with these years, you can see the curves actually drop much faster for these 2 years. Whereas here, the snow melts out slower. One reason this might be is we might have had a cleaner snowpack this year. So this is where we talk about the albedo of the snow really mattering, where for the same covered area of snow, if the snow is more reflective, it's not going to melt as fast. So this is an example where you might have started out with about the same amount, but the direction the melt went was actually quite different. And for these 2 years, you can see the melt out date is about here. And for this year here, when we follow it out, our melt out date is much later in the year. And then we can see here too, we had a really big year, but in this really big year, it actually melted faster than the year that wasn't quite as big. So this is where it becomes really useful when you have these many years of information. You can start to learn a lot about what's going on in the mountains. And right now in this lab, just to kind of fit it all on the internet for the lab for everyone to use, there's just 9 years of data for this one basin. But we can really use these data for the last 20 years, and we can do it across all of high mountain Asia, all of the Western US. The scale at which we can look at stuff like this is really big, and this is a really powerful tool. So anybody have any questions about these SWE depletion curves and looking at all the years at the same time from SWE reconstruction? Okay, so now what we're going to do is we're going to look similarly to how we looked at the snow-covered area plots. Now we're going to look at, here we're just showing kind of the depletion in the basin over time. Now what we're going to do is we're going to look at each year, the SWE, how it's distributed in the basin, compare that to an average year, and then look at all the years at the same time and see if we can start to see trends and differences in the individual years. So for this, what we're going to do is we're going to look on April 1st. April 1st is kind of the default day that people tend to think of as the start of the melt season. But it's not always the day each year that melt starts. So we're going to pick the 1st of April. And what we're going to do is we're going to take, for these 9 years of data we have, we're going to make this empty data cube that we're going to fill with what the snow water equivalent was in each pixel on this day of the year for each of the 9 years in our record. So first we're going to do it for the average SWE. So let's see, run this. Yep. So what I did here is I calculated that. So our record, SWE record, this is our empty variable we created to hold our data. And then I load up the SWE for each year. This is just a point for everyone. I mentioned we're loading in all this satellite data with the raster IO function. Like I said before, we open it first, and then we read in the data. Before, what we were doing is we were reading in all 365 days of data. If you put in a specific day you want right here, you can actually just read in the exact day you want the information from. So that's kind of a useful tool with Python, where you can load, you don't have to load all the data in from a GeoTIFF at once. You can just load in the day you're interested in. And then we're filling up our array with all the SWE data. And once we add this, we also found the average. So just what the average amount is in each one. So let's look at the mean SWE really quick and see what it looks like. So this is our map of the basin with kind of the average amount of snow water equivalent across the 9-year record in each of the pixels. We can see that there's really not much contributing to snowmelt at the lower elevations. And then at the higher elevations, we have areas that tend to be kind of hot spots and contribute a lot of the melt. And then we can even see kind of some characteristics of the topography of the mountains in this basin, where we can see that the northern slopes tend to hold more snow than the southern slopes do. So now question we had before, now that we're going to look at SWE for a given year and compare it to the mean amount of SWE in the pixels, what do you guys think a good color map, type of color map to do that would be? Do you think it'd be the same or different as the one we used for the FSCA? We probably want to use a similar type of color map where we have a diverging color map. And we're going to use a different one this time. So up here, just to remind you, we used this color map with the greens and the pinks. Just to give you guys some exposure to another type of color map, I'm going to use this other color map. Where is it? It's called SWE, and that is, if we just look really quick on Color Brewer, we're going to be using, which one is it? Oh, I don't even know where it is. It's one of these. I don't see it. Okay. So let's run and see what it looks like. So this is a color map where it goes from yellow, where we have lots of SWE, to blue, where there's less SWE. So here we have, for 1 year, we've made a map where we take the SWE for 1 year and we subtract the average SWE from it to get this map, where we can see, okay, for this year, we had more SWE in some of these spots and less SWE in some of the other spots. So this is kind of useful looking at one map, but one really powerful thing we can do is what I want to do next down here, which is look at all the years at the same time. And when we do this, we're going to set the color map to be the same for every year. So a yellow color in one map is going to mean the exact same value as a yellow color in another map. And what we've done now is we have all 9 years of data we have here, and we can look at how each of these 9 years differed from the average amount of SWE we saw in the basin. And this is really cool. And this is where we can start to see what happened each year and how it might be different and matter differently. Where we can see in one of these, this wet year, we had a lot of the snow water equivalent kind of being generated up in this portion. Whereas in some of these other years, you can see maybe more of the snow is coming from other regions in the basin, or down here over here. And then in this year, 2011, you can see that there's significantly less snow in the upper regions of the watershed up here. So it looks like there was far less snow water equivalent up in this part of the watershed. And so this is a really kind of cool way to visualize this reconstruction each year and kind of start to get a sense of what might be going on up in the mountains. And so this is a way of looking at it compared to the average. Another really useful way to look at this is we can just look at the actual amount of water in the snow each year on a date. So I'm going to show you that here, the last graph in the lab. And this is visualizing the reconstruction data where we're just looking at the raw amounts. And also really informative. You can start to see kind of where the water's coming from in this basin. And you can see that there's some variability from year to year. And there's also spots where it tends to come from over and over again. So this is really kind of a cool use of this reconstruction data for looking at kind of the fine scale of differences and variability and where the SWE is coming from. So that we have 2 minutes left about in the lab. I don't know if, Carl, do you have any kind of caveats or details about SWE reconstruction you want to mention really quick?
Well, I guess we'll just open it up for questions while I think
Okay.
about that. So,
Cool.
so feel free to type any more questions into the chat or unmute yourself and ask. In the next lecture, we'll talk a little bit about how we can get to a finer spatial resolution maps. It's worth noting that we're already at 500 meters, much, much higher than the passive microwave and much higher than sort of the global models from ERA 5 that we looked at. But there are opportunities to take this even higher with the optical remote sensing, and we can calculate the energy balance at any scale from 500 to 1 meter resolution. So moving forward, it's more nations are launching satellites that allow us to view snow cover and the active radar as well we have. And you know, I think looking backwards, we won't always be able to resolve SWE the way we might be able to in the future, but the historical context is still a pretty useful tool.
Yeah, and then I see Amrit, you have a question?
Yeah. I have question related to beer. So, Carl, have you also developed MODIS product from beers, or it is only from MODIS?
Yes, so we've tested beers. We haven't produced any long time series, although we have done, I think, just 1 year of data that's for sort of the upper Indus River Basin. And I actually just finished the proofs on that paper today. I will add that to the chat window as well. The link will just have the abstract. It won't have the full paper yet. We're still waiting for some additional funding to apply it and actually produce the products, but I expect that will likely happen given sort of the success that these products have had in the use that they've had in the past. So it's, I guess to say about VIIRS, I could say a few things, which is that, it's slightly coarser resolution than MODIS, but it has some additional features. They do some pixel trimming at the edges. So when the off-nadir views, it doesn't include so much of the area as Timbo had described. And I just pasted that link in the chat there. So even though it's slightly coarser resolution, it appears to map snow just as well as we have been mapping snow with MODIS. We haven't looked into the albedo yet. With the mixed pixels, we can expect possibly similar results because of the modeling that we do. At the lower snow fractions, it could be a little more challenging, but we've yet to sort of do that analysis. And we're hoping eventually that the National Snow and Ice Data Center will be processing and producing these globally. It takes time to convince everyone and get everyone on board and get the funding to do that. And we're working on doing that so we can share, the best available products with everyone in the world.
Awesome. Does anybody else have any questions? We're at time now. We'll definitely take if there are any more questions.
If you weren't able to watch the last lecture, please do, and we'll take questions in the final training session from any of the past work. We're happy to do that and answer anything. But the last lecture had a lot on the reconstruction and quite a bit of detail on the energy balance. Some of you may look at all the equations and sort of be overwhelmed, but we do have our energy balance model available on GitHub. So I will post a link in there. Ned Bear has that on his page.
I'm showing you guys right now where it is. So you guys can keep talking, Carl. You can
yeah, so you don't have to do all the work. We've done the work and we have a model that's available to do the reconstruction. The hardest part about this is preparing the inputs, the sort of the MODIS data and the reanalysis data. And the reanalysis data right now is available. You can download that freely as part of a NASA High Mountain Asia project, which we'll talk a little bit about in the next lecture. We're working on producing these for 12 MODIS tiles that I've shown in a previous slide, and I think maybe 2 of the lectures. So, yeah, I think, having folks who are local, be able to use these modeling efforts is useful. We're also, we'd be excited to collaborate with folks who have on the ground measurements to compare to our modeling efforts. So yeah, that's it.
All right, last call for questions for this morning. Okay, well, thank you everyone for coming again today. This was really useful. I hope you found it useful. If you have any questions, feel free to write them down, and we're happy to go over any material from any of the labs on our final session on Wednesday. So on Wednesday, what we're going to do is we're going to do the last lab, and then there was a portion of the first lab that we didn't have time for. We're going to go back and look at that also. So with that, we're going to turn it back over to Rajesh, and I just want to say thanks everyone for tuning in today and for joining us with going over the material. I hope it was useful.
Thank you very much, Timbo and Carl, for delivering excellent lectures and then also responding all the queries of the participants. I'd like to thank participants also for their active participation in this training. And maybe in a couple of hours, we are going to share the other the lecture video and also the training videos that we conducted today, so that if any of the participants was unable to attend this training right now, and they can practice later. Thank you. So we can close today's session. Thank you so much.
Okay, thank you everyone. Have a good rest of your day.
Thanks so much.
Thanks, Tim.